theories of things. We are going to start from the things that we know, right? All of us know the periodic table, right?
Mm-hmm.
You know what the periodic table is. It's the table of the elements. And I would like to say that the periodic table, you can think of it as the first database of information that we have. It's a table that we organize information according to the properties of the elements, according to the properties of the atoms of the elements. And the important thing from the periodic table that we need to know is the names of the elements, right? These are specific things. We know the names of the elements, we know the symbols of the elements. You are not going to be tested on the names of the elements or the symbols of the elements, but when I write the letter O on the board, I expect that all of you know that O stands for oxygen, right? So when we write simple chemical formulas, you expect yourselves to know these things, and also to know the difference between the atomic number, and the mass number, right? All these things, elementary things that you learn. The important thing that we are going to start here today is with the electronic configuration of the elements. Okay? Electronic configuration of the elements. Okay? And when we say electronic configuration, we essentially refer to the organization and the placement of the electrons in the energy levels around every atom, right? And we are not really going to go to the elements with 100 and 200 electrons, although these elements are also very important. We are going to start with the small elements, the elements that are important to us. And the elements that are important to us is the hydrogen, right? How many electrons does the hydrogen have? One electron. So the electronic configuration of the hydrogen is 1s1, right? 1 is the main energy level, right? The main quantum number as you learn in general chemistry. S is the sublevel. So level, sublevel, and from the sublevel, we also go to the orbitals. And 1 is the number of electrons that are in that S sublevel, right? The second one, the second element in the periodic table is helium. And of course, helium now is 1s2, right? We have 2 electrons in the S sublevel. Now, when we talk about the sublevels, let's just remind ourselves of the sublevels. Most of the sublevels that we are going to be dealing with is the S, and how many orbitals? AO stands for atomic orbitals, okay? So let me write it here, atomic orbitals. So how many orbitals does the S level have, the S sublevel have?
2.
Orbitals, not electrons. 1. The S sublevel has 1 orbital, the S orbital, okay? The S sublevel has 1 orbital, the S orbital. Now, the next sublevel that we have is the P sublevel. We can go to the next orbital here, to the next element. I'm going to have lithium, right? Lithium has an atomic number of 3, so it's going to be 1s2, and then we switch, we go to the next period, and it's going to be 2s1, right? And then, if I go to the next one, after lithium is beryllium, we are going to have 1s2, 2s2, right? And we keep going. All these small elements with a small number of electrons. I want to take it to the boron, carbon, nitrogen, and oxygen, right? So the boron has another electron. So helium has 2 electrons, this one has 3, beryllium has 4, boron has 5, carbon has 6, nitrogen 7, oxygen has 8. And if we want, we can also put fluorine somewhere here. Fluorine has 9 electrons, right? So if I draw the electronic configurations of all these, I'm going to have for boron 1s2, 2s2, 2p1. And carbon is going to be 1s2, 2s2, 2p2. Nitrogen 1s2, 2s2, 2p3. Oxygen 1s2, 2s2, 2p4, right? And the fluorine is going to be 1s2, 2s2, 2p5. Okay. Now, going along, you can see the s orbital, the s sublevel has 1 orbital, and every time the orbital or the sublevel takes 2 electrons, we move to the next level, right? So conclusion, how many electrons does one orbital take? 2. So one orbital takes 0, 1, or 2 electrons. Okay? So it takes maximum 2 electrons. It can have 1, it can have 0 electrons, right? So that is important, yes.
I'm so sorry, but when you talk about this, you're talking about the rings, right?
We didn't go there.
Oh.
We are getting there. Don't worry. We need to review what we know, and then we are going to bring in the shapes. The shapes are very important too, because they explain a lot of things. Okay? So the s orbital we can see for 1s1, 1s2, 1s2, and the third one goes to the 2s1, right? To the next level. Okay? After it takes 2. Then we put 2 on the 2s, right? Again, energy level, energy level, energy level, energy level, right? Energy level. The 2 is energy level. Okay? The S is a sub-level. All the S's are sub-levels. Okay? And then the orbitals are the follow up. Now when you complete the S orbital of the second level, then we go to the next sub-level, because the second level of energy has 2 sub-levels, right? So the second level of energy, the 2s, right, is the second level of energy. It has 2 sub-levels of energy. The 2 sub-levels that we have are the P, the S, and the P. So when the S is completed, the P begins picking up electrons. And if you remember from your general chemistry, all the times when we have a group of orbitals to fill out, then we put 1 electron to each orbital first, and then we pair them, right? So how many orbitals does the P have? The P sublevel has 3 orbitals: the Px, the Py, and the Pz, right? So we have 3 orbitals. Therefore, 3 orbitals. So what is the maximum number of electrons that we can put on the P or the P sublevel? 6. So it can go from 0 to 6 electrons. Okay? So that's something that we need to understand. The S sublevel has 1 orbital, the S orbital, and it can take up to 2 electrons. Each orbital can take maximum 2 electrons. The P sublevel has 3 orbitals: Px, Py, Pz, and each orbital can take maximum of 2 electrons. That means we can place on that p orbital up to 6 electrons. Now, when we do the placement of the electrons, there are some rules. I don't really want to remind you the rules. So if we are going to put them like that, as the same sublevels, right? For this, and for this, and for that. What we do in each one of them, when we start placing the electrons, this is the 2p1. It doesn't matter on which one, you just put 1 electron on 1 orbital. Then you have 2 electrons. You are not going to put them together on the same orbital. You are going to spread them. You are going to put 1 electron on each orbital, right? When you go to the p3, you are going to do this. Okay, and when you go to the oxygen, which has 4 orbitals on the p, or 4 electrons on the p orbitals, you put 1 in each one of them, and then you put another one, and you pair it, right? And if we do the same thing for fluorine, 1, 2, 3, we are going to have 1 in each, and then we make 2 pairs. So that's basically the electronic configuration of these elements. And I'm sure if we continue, you can go on and you can remember everything that you learned about these things. What I want here now, before we go on, I want to introduce you to the shapes of the orbitals, right? The s orbital, and you can think about it, the s is the first initial of the word sphere, right? You can connect it that way. The s orbitals are spherical orbitals. They are little spheres. So when we have the s orbital, the s are like that, okay? So like a sphere, or like a globe. That's the s orbital. The p orbitals, the p is the first letter of the word planar, right? The p orbitals have planar symmetry, okay? What do you mean planar symmetry? It means that we can have a plane, a mirror, that can divide the orbital into 2 identical parts. This is why the p orbitals look like that. And this is the plane that divides the orbital into 2 identical parts, right? The one, and usually to distinguish between the 2 of them, because they have opposite polarity, we put the one as a positive and the other as a negative. Now, this is the 1 orbital, it doesn't, 1p orbital, it doesn't matter which it is. It can be the px, the py, the pz. They have the same shape. Okay? Doesn't go high. Okay. Now, before we go on, I just want to give you the shapes of the d orbitals. The next level is the d energy level, and in the d energy level we have 5 atomic orbitals, and that means the d energy level can take from 0 to 10 electrons, the same way that we have them over there. The 4 d orbitals, d is the first letter of the word diagonal, which means they have diagonal symmetry. So the 4 d orbitals are essentially looking like that. Okay, 4 d orbitals like that, they look like that, and the 5th d orbital looks like that. This is the 5th. 4 d is like that, the 5th d orbital like that. And each one takes 1 electron, or the maximum 2 electrons, to make the 10 electrons of the d orbital. In order to find the d orbitals, you need to go to the next and next energy level, the third period of the periodic table, the third energy level, and the fourth energy level, basically. Okay, so what I want you to know is the way that we do the electronic configuration of the elements, the relationship between the orbitals, the s orbitals, and how many electrons they can take, the p orbitals, and how many electrons they can take, how we can fill them up, how we can put the electrons in the orbitals, and very important, the shapes of the orbitals, because I'm going to use the shapes in the next one as, to explain some other things when we move on. Okay? So, now knowing these things, we go to the how we use the electrons, what we use the electrons for, right? The electrons are like, when it comes to chemistry, the electrons are like the dollars that we are using in our everyday life. We give dollars, we take dollars, right? So the elements, they give electrons and they take electrons. Or sometimes we share dollars, we become partners, so we share our resources, we share our dollars. And sometimes the elements share their dollars, their electrons as well. So we use the electrons to make chemical bonds. And if you remember, we have two kinds of chemical bonds. We have the ionic chemical bonds, and we have the covalent chemical bonds. Okay? The ionic chemical bonds are forming by giving electrons, and gaining electrons. An element that gives, or an atom that gives away electrons becomes louder, positive, and then a term is cation. So, for example, lithium gives away one electron, becomes lithium cation, right? And an element that takes electrons, like chlorine, for example, is going to take one electron and is going to become an anion. Okay? So the positive charge indicates the efficiency of electrons, and the negative charge indicates excess of electrons, right? So let me point it here. Efficiency excess. And when I say efficiency, remember, when you have elements, when you have neutral atoms, the number of the electrons equals the number of the protons. So when I put one positive charge, it means that the positive charge is the number of the protons.
Thank you.
I forgot to do that. The number of the protons are one more than the number of the electrons. When you have a negative charge, it means the number of the electrons is one more than the number of the protons. Okay, so everything depends on the comparison between the number of the electrons and the number of the protons. Now, covalent bonds. When you go to the covalent bonds, we have sharing of electrons. When we have covalent bonds, the atoms don't give away their electrons, they don't take away from other atoms, they share them, they pull their electrons together to make the chemical bond. Example, hydrogen has one electron with another hydrogen atom, they share a pair of electrons, right? The hydrogen with chlorine chlorine has 7 electrons. So hydrogen will share with chlorine. Or I can do also the same thing with nitrogen. Nitrogen and I'm going to make okay. So now when you have the sharing of electrons, sometimes like in our lives we have equal partnerships, or we have partnerships that are not very, very equal, that one partner is cheating the other, right? So we have equal sharing and non-equal sharing. So if I go to these examples that I have over here, when I have the hydrogens, am I having equal sharing of the electrons?
Yes.
Yes, this is equal. And here, am I having equal sharing?
No.
No, not equal. And for the nitrogen, am I having equal or not equal? Equal. Okay. So the next question is, what makes the sharing of electrons equal and what makes it not equal? Electronegativity difference, right? So when we have homoatomic, we have equal share. Or when we have no difference in electronegativity. So we have equal sharing, we have the same elements sharing the electrons, right? The same element sharing the electron. So we have no equal sharing. When we have different elements sharing the electrons, we have not equal sharing. And when we have homoatomic, we have the non-polar bonds, and when we have heteroatomic, we have the polar bonds, right? This is heteroatomic here. Heteroatomic means different atoms, okay? So, pushing this one up. And bringing this one down. Let's go back to those last structures that I created. Okay, I had nitrogen. Okay, and another nitrogen. Okay, what do we call this kind of presentation? Lewis dot structure, right? And I put 5 dots around the nitrogen. Those 5 dots indicate what we indicate. Lewis dot structures. And those dots indicate the valence electrons, right? And the valence electrons are which electrons? The electrons placed on the outermost energy level, right? Okay. Outermost energy level. And what is the relationship of the valence electrons with the group that the element belongs to? They are the same. Okay? So if the element belongs to group number 1, has 1 valence electrons. If it belongs to group number 2, has 2 valence electrons, 3, 4, 5, so forth, right? So now these are the Lewis dot structures, and if you look up there, I put them in such a way that I have 6 electrons between the nitrogen, right? I have 6 electrons. So the question is, what does drive the formation of the chemical bonds? Why are the chemical bonds forming? Why do the elements, I don't want to say feel the need, why do the atoms of the elements are driven to form chemical bonds, either by losing electrons or gaining electrons or by sharing electrons? Stability is correct, so they become stable when? They want to have 8 electrons in their valence shell. And there are 3 ways of achieving that. Either they are giving away electrons to go down to have 8 electrons. They take electrons to build up and make the 8 electrons. Or they share electrons, right? And it doesn't matter at this point whether the sharing is equal or unequal. So elements in the first and the second and the third group, they give away electrons to form cations +1, +2, and +3 in order to go to the lower energy level, which is going to have 8, the noble gas, 8 electrons. Elements in the groups 5, 6, and 7, they take 3, 2, and 1 electrons to form anions with -3, -2, -1 to make the octet rule, or elements like nitrogen, hydrogen, oxygen, nitrogen, so forth, they share electrons to make the octet rule. And when we say octet rule here, let me demonstrate it for people. So these are the 6 electrons. They are controlled by this nitrogen, so 6 + 2 are 8. And those other 6 electrons here, they are controlled by the other nitrogen, so they are 8. So the 6 electrons in between the nitrogens are controlled by both elements, by both nuclei, so both of them at the same time fulfill the octet rule. So let's do, we have, I put over there before the chlorine, right? And I'm going to give you now the oxygen. And I'm going to give you the nitrogen. With hydrogen, right? Okay, okay, let's do also one with carbon. Okay, so these are some of the basic compounds that we live with every day. Hydrogen chloride. I have the chlorine here controlling the 8 electrons, right? And then the hydrogen and the helium are the only elements that in order to be stable, they need 2 electrons, right? So the hydrogen has the 2 electrons. In every compound that I put here, the hydrogen controls the 2 electrons, right? And the other element, what we are going to call the central element, controls the 8 electrons, right? Oxygen is the central element in water, has the 8 electrons. Nitrogen is the central element in ammonia, has the 8 electrons. So before we go on, let's identify these kind of electrons that we have over here. So if the electrons are shared between the two elements in the chemical bond, like those over here, those are called bonding electrons. Okay? If they are not shared, like these pairs, okay? These pairs. Those pairs that are not shared, they are called lone pairs. Lone pairs, or the term that is better describes them, non-bonding pairs, or non-bonding pairs of electrons. Okay? It's important to be able to recognize that. So, here we have bonding electrons, two bonding electrons, two bonding electrons, two bonding electrons, two bonding, two bonding, two bonding. How many bonding electrons do we have here? 6 bonding electrons. And this molecule that I put over there, the carbon is the central carbon, right? It has 4 electrons on this side, 4 electrons on this side, and it has the non-bonding electrons on the oxygen. And each oxygen, if you count them, they account for the 8 electrons on each element. Okay? Now, 6 electrons. How many bonding electrons do we have here?
4.
4. 4 bonding electrons. Okay, and here we have 2 bonding electrons, right? 2 bonding electrons. So how many electrons do we need to make a chemical bond? How many electrons do we need to make a chemical bond? Let me rephrase the question. How many electrons do 2 atoms need to share in order to have a chemical bond between them?
4 or 8?
2. We have a chemical bond here, they share 2 electrons, right? We have a chemical bond here, they share 2 electrons. We have a chemical bond, they share 2 electrons. Chemical bond, they share 2 electrons. Chemical bond, they share 2 electrons. Here we have 4 electrons. So if 2 electrons are 1 bond, the 4 electrons are double bond. We are not going to violate the English grammar, okay? If you have 1, you double it, it's double, right? Double. It's a double bond. Okay, and if we have 6 electrons, it's a triple bond. Okay? So now that we understand the implication of the English grammar in chemistry, okay? We have 1 bond, we call it single bond. It requires sharing of 2 electrons, okay? Double bond is sharing of 4 electrons. And triple bond is sharing of 6 electrons, okay? Now, because now I'm sure you know how to draw and use that structure, right? You know how you connect the various electrons with the element, and then you can go on to draw them and connect them. But because we are going to be dealing with molecules and a lot of sharing of electrons, we are going to take the easy way out. For every bond, we are going to draw a bar, right? Like that. So that's the drawing. For the double bond, we are going to have two bars between the elements, between the symbols, and for the triple bond, we are going to have three. For example, when I do the hydrogen, I can draw that one. When I do the water, I can draw this. When I draw the triple bond for the nitrogen, I can draw one. When I draw not the water, the carbon dioxide. That's my molecule with the double bond, right? The carbon dioxide. Now, when I do that, I presume that the lone pairs, that all of them have the octet rule. Octet rule is satisfied, meaning that if I don't show the electrons, they are lone pairs of electrons, non-bonding pairs of electrons to satisfy the octet rule. And most of the times, we are not going to be using the Lewis dot structures. We are going to be using bars to indicate pairs of electrons. So I can put two bars on the oxygen, and these are the non-bonding pairs of electrons. And I'm going to put two bars over here to complete the octet rule for the nitrogen. So we will be using mostly the bars between the elements, the symbols of the elements, to indicate the chemical bonds. If sometimes we are going to be putting the non-bonding pairs of electrons, but if we don't put them, that means they are there to fulfill the octet rule for the element. Okay? Now, now we are going to talk about the carbon. After all, we are going to be doing organic chemistry, and organic chemistry is the chemistry of the carbon compounds. And there is a reason why you have a whole area of chemistry dedicated to the carbon compounds. Because most of the molecules that we have around us, and most of the biological molecules that we are using, they are made of carbon compounds. They are millions. We know of more than 8 millions of organic molecules that are made of carbon compounds. And they start from the simpler ones, and they go all the way to the most complicated ones. Let me give you some of the simpler ones. Methane, for example. It's a molecule with carbon and hydrogen. It's a very important molecule because this is basically the molecule that we are using to cook our food, as in the big cities like New York, where you go on and turn on the stove and heat starts. You are burning this molecule. When you do your house, the heating of your houses, of your apartments, is based off the reaction with this molecule. Another molecule fairly simple, if I replace the hydrogen with chlorines, carbon tetrachloride, that's another molecule, quite simple, quite useful, but also carcinogenic. People who are exposed to it, and we can have a whole discussion about it. Another one, people that we are using, this molecule, formaldehyde. And these are 3 of the smallest molecules that we can have with the carbon, right? The question is, and we can have molecules with carbon that are made very long. Now, before we go there, let's say a few things about the structures of the molecule. In your general chemistry, you had a way of determining the structure of the element of a molecule based on the number of the pairs of electrons and the number of those connections they have, right? Right? And anybody remembers the method? If I remember correctly, remember I did this one many years ago. VSEPR, right? This is basically the approach. You use the valence electrons, you identify a central atom, and you decide how many connections you have. So we have a central atom. Based on the central atom, let's say in our case is carbon, and if it has 4 connections connected to 4 atoms, and a central atom with 4 connections is this molecule and this molecule over there, right? So what is the structure based on this molecule? If we have a molecule connected with 4 atoms, no lone pairs, no nothing, the structure is tetrahedron. And it's not because somebody decided that it's tetrahedron, right? It's the structure, it's the only geometric structure that can divide the space around the central atom into 4 equivalent identical spaces. Okay? The tetrahedron is this molecule, is this. Let's start with it. Tetrahedron is essentially a pyramid, a trigonal pyramid with 4 faces being triangles, equal triangles, right? So if you consider that one, in the center of the tetrahedron be the carbon, okay, and at each corner you have a hydrogen. So when you look at the molecule, you are not going to look at the wide pyramid, the triangles. What you are going to look are the bonds from the carbon to the hydrogen. And we know that they are at the corners of the pyramid because the angle between those, these angles, these 4 angles are identical. The length of the bonds is the same, the angles are identical, and they correspond to the tetrahedral structure. Okay? Angles are 109.5 degrees. So every time we speak about the tetrahedron and the tetrahedral structure, these angles are going to be 109.5 degrees. Now, let's say the central atom has, central atom has 3 connections and 1 non-bonding pair. Okay? 3 connections with 1 non-bonding pair. I can put the same thing. Basically, I go here and take 1 hydrogen away, right? So let me do it. I do the carbon. I'm going to use a different color. I'm going to do the carbon, right? Hydrogen, hydrogen, hydrogen. And over here, the top carbon, I take it away and I have a lone pair of electrons, a non-bonded pair of electrons, right? Now, if I do that from this one to that, this one is going to be an anion, right? So an anion, although they exist and we can create them with the carbon, we are not going to go on to them. But if I replace the carbon with nitrogen, if I replace the carbon with nitrogen, Okay? One pair of electrons, non-bonding pair of electrons, 3 bonds. Nitrogen fulfills the octet rule. Which molecule is this one? It's a trigonal pyramid. Pay attention to what I'm asking. What did I ask? Which molecule is this one? I didn't write which structure.
Is it a mole?
Okay? You anticipated the question,
It's
but I didn't ask what is the structure. I asked which molecule is it. I want you to connect the molecule first and then the structure. Ammonia. This is ammonia, right? And you are right. It's a trigonal pyramid. Okay? Now, let's stretch, let's push this, right? 3 bonds, 3 connections. No, 0 non-bonding electrons. I take this one away, right? If I do that, I'm going to go down to boron, and we are going to have basically, I'm just going to put chlorine here. With the hydrogen exists, but also with chlorine and everything. So we are going to have the borane, okay? And this one is trigonal planar. And here is, let's share a little secret. Ammonia is a stable molecule, right? Right? If you did your lab experiments, you had a bottle which said ammonia, ammonium hydroxide, right? Ammonia is a stable molecule. It's gas at room temperature. It's a very nasty molecule, smells very nasty. But at minus 33 degrees Celsius, you can see it as a liquid. It's a stable molecule, in other words. This one, the borane, is not stable. We can make it, we know we make it, but we cannot really have it. It can be stable in the gas phase where one molecule is far away from another and doesn't have opportunity to react with anything. Why is not stable? Ammonia is stable, this one is not stable. Actually, that one dimerizes very fast. It doesn't exist in that. Okay? The first opportunity is going to attach itself to something. Why is not stable? Exactly. It doesn't fulfill the octet rule. Boron has only 6 electrons. Okay? 6 electrons. Here we have 8 electrons. So if a molecule doesn't fulfill the octet rule, if the central atom doesn't fulfill the octet rule, then that one is going to be very reactive. It's going to be less stable and it's going to be very reactive. Okay. 2 connections and 2 non-bonding pairs. Okay? In other words, what I do here, I take another hydrogen away, and I'm going to make the long story short. I'm replacing it with hydrogen. I'm replacing the 2 lone pairs, the central atom with oxygen, to make it stable. It's not that if I take away one of this hydrogen, it's not going to be the ion, we can form the ion. But if we do that, we are going to still have the non-bonding pairs, the hydrogen, right? Okay. Now, and the shape of this molecule is bent or angular, right? Angular is a better word. It reminds you of the angle, so the things are going to be the elements are going to be at the angle. Okay, now we made the connection going down from this to that. And the angles between, this is 109.5. What should be these angles? They are going to be similar. I don't want to give you the wrong information. The angles between ammonia, between the hydrogens in nitrogen and the hydrogens in the water, they are similar to the tetrahedron angles. They are not 109.5. They are a little smaller, 108 or 107 or something, right? And you may ask, how do you know that? There are people who actually measure them, right? We can crystallize the molecules, put them on an X-ray crystallographer, take a picture of the molecule, and then measure the angles. So we have no doubt about these angles. And they are smaller. These are a little smaller than the 109.5, they are 108, because the pairs of the electrons, they are pushing the bonds to close in. Not a lot, but the point is that all of them have similar structures. The central atom is close, the angles are close to the tetrahedron structure. When we go over here, we have the triangle, the trigonal planar, and these angles over here are going to be 120. Okay? We divide the space around the central element, and they are going to be 120 degrees. So, we go starting from the carbon. We can see the carbon over here with 4 single bonds is a tetrahedron structure. Then we have the carbon with a carbon-oxygen double bond, right? So, what is the structure of this molecule? What is the structure of this molecule? Carbon has connections with 3 elements, right? And this one is also going to be trigonal planar. And the angles over here are going to be 120 or close to 120 degrees. And I want to give you, that's one. I'll give you another element, another situation with the carbon, where we have the carbon now. These are the 8 electrons, right? The nitrogen has its own 8 electrons because it has a lone pair here. And based on, to our model, we know that this one is trigonal planar because we have 3 connections around the central atom, no lone pairs, no loose lone pairs, no bonding pairs. And here we have around the central atom 2 other elements and no lone pairs on the central atom. And this one is a linear molecule. Linear molecule, which means that this angle over here is 180 degrees. Okay? So we saw the carbon forming a tetrahedron, forming a trigonal planar structure, forming a linear structure, right? Okay. Now we are going to go into the magic of the carbon. Question is, how does carbon do that? Or how does carbon do that? How does the nitrogen do it? How does the oxygen do it when they go into the tetrahedron? Okay, so let's go back to the basic electronic configuration of the carbon, and we take it from there. Okay, electronic configuration of the carbon, right? we said that the carbon has 6 electrons, right? And the electronic configuration of the carbon is 1s2, 2s2, 2p2, right? Which means the valence electrons of the carbon are distributed in 2 different kinds of orbitals, in 2 different energy levels, right? And if we want to do it, this is the S, the 2s has 2 electrons, and the 2p that have 2 electrons. And we know now, and here is, we know that when we form the tetrahedron, right? When we form the tetrahedron, we form 4 identical chemical bonds. So how do we explain that? How does carbon do it? Because this configuration here tells us that it's going to have to form at least 2 different kinds of bonds. One bond with the p orbitals and one with the s orbitals, right? But here it forms 4 bonds identical with the right angles and everything. So the way that we explain that is, this is the ground state, this is how it starts, and this is the atomic orbitals, right? But these orbitals are not the ones that are used to make the bonds. What we are using hybrid orbitals, hybrid atomic orbitals. To make the chemical bonds. And those hybrid orbitals are a combination of the s and the p atomic orbitals. So what we are doing here, we are mixing the p orbitals and we are mixing the s orbital to make 4 hybrid orbitals. Why 4? How many orbitals are we having here? 3 p's, right? And 1 s, that's 4 atomic orbitals, right? So the 4 atomic orbitals will create 4 hybrid orbitals. Okay? And because we are mixing 1s and 3 p's, that these hybrid orbitals are going to be called sp3. 1s and 3 p's, right? So we are mixing these orbitals to make the chemical bonds, to make the orbitals that are going to share, are going to have the electrons for the chemical bonds. So I'm just going to give you an idea how we are mixing those. Here is the s orbital, right? And in the s orbital, I'm just doing it for 1, right? This is one of the p orbitals, right? So let's say that the s orbital has a positive sign and the p orbitals, one is positive, the other is negative. So think about it. If we are going to mix them together, the part of the p orbital that is above is going to be reinforced by the positive of the s orbital, and the part that is below is going to be weakened, right? So this one now is going to become this orbital. Okay, this is how the sp3 orbitals look like. So the sp3 orbital is going to look like a huge balloon with on one side and a weaker balloon on the other. If I do the same way that I do for the sp3 orbitals, I'm going to make 4 identical single bonds. Okay? Now, if I don't need 4 single bonds, 4 identical single bonds, And in the case that we have up there, we need a double bond and a triple bond, right? So I can use 3 atomic orbitals to do the the blending, to do the hybrid, in which case I'm going to use sp2 hybridization, and for the sp2 I am going to make I'm going to make 3 sp2 orbitals. Here I'm making 4 sp3 orbitals, right? And if I use 2 atomic orbitals, I mean, when I'm going to use the sp, right? And I'm going to make 2 sp orbitals, right? To make the here I'm going to make 1 double bond plus 2 single bonds. Here I'm going to make 1 triple bond plus 1 single bond. Okay? So, let me push it up. The shapes of the hybrid orbitals are going to be the same as the shape that I put over there, right? I'm just giving you a perspective to get the idea. So I'm just going to clean here. So let's put again.
Sir, what does the 1 triple, 1 single mean again?
We're going to write them here again, right? So let's see. We have the atomic orbitals, right? And I can use the s and the p orbitals, right? So if I use the 1s and the 3 and the p orbitals, I'm going to make hybrid orbitals, hybrid atomic orbitals. And what I'm making, I'm going to make 4 sp3 orbitals. Okay? And the 4 sp3 orbitals, they are going to correspond to the tetrahedron structure of the carbon, right? Basically 4 single bonds. If I use the S and 2p, right, 2 of the p's, not all 3 of the p's, I'm going to make 3 sp2 hybrid orbitals, and I'm going to make the double bond. I'm going to have a carbon with a double bond. This is tetrahedron. Four single bonds. I'm going to make 1 double bond, or the carbon will have 1 double bond and 2 single bonds attached. Okay? And the structure is going to be trigonal plane. And if I use only 1s and 1p, I'm going to make 2 sp orbitals, right? And the structure, I'm going to have a triple bond and a single bond. 1 triple bond and 1 single bond. And the structure is going to be linear. Okay? Now, how many total bonds we make here for the carbon? Okay, when we say we need the carbon, how many bonds we make on the carbon? Somebody brave enough to say four? Four bonds, right? How many bonds we make here? One double plus two single. How many total? Four. And how many down? Four. So in every case, in every instance, the carbon makes four bonds. Okay? So in all the molecules that we are going to be looking in the organic chemistry, we are going to be looking, at least when they are neutral molecules, the carbon is going to have always four bonds. It doesn't matter whether they are going to be double, triple, or single, all the times they are going to be coming up to be four bonds. Examples. We said the methane before, right? This is methane. If I attach on this carbon another carbon, I'm having two. Both carbons are tetrahedral. Both of them are sp3 hybridized. I had before the carbon with oxygen double bond and hydrogen, right? If I replace the oxygen with another carbon, okay? Both of the carbons, if you count the number of bonds around the carbons, they are always four. And this is 120 degrees angle. These are 109.5 degrees, and these are 120 degrees as well. And if I replace, I will put before the hydrogen with cyanide, right? You know hydrogen cyanide, right? The very poisonous thing, right? That people, when they make it, don't live to regret it. This is hydrogen cyanide, triple bond, single bond. If I replace the nitrogen with a carbon, I'm making this molecule, right? Again, four bonds. Acetylene. This is acetylene. It's one of the main industrial products. When we burn it, it generates very high temperature. It can cut through steel. Now, couple of more minutes, okay? And then I let you go. I want to make a good impression. Because now, and you saw that it took me a couple of minutes to draw these molecules, I'm just going to give you, to let you go with an easy way to draw these molecules. We're going to start from here on Tuesday. When we draw the molecules, when I draw this kind, this is what we call a complete structure. It shows all the symbols of the elements. It shows all the chemical bonds in the molecule, right? Now, I can write this one this way or this way. This is what we call a condensed structure. It shows the symbols of the elements, right? But it eliminates the chemical bonds. And if I go down, okay, this one where I just show the symbols of the elements and how many they are, this is what we call a molecular formula, right? So I'm going to give you now a bigger molecule. I'm going to make a molecule with 4 carbons. 1, 2, 3, 4. Okay? And it took me like a few seconds to draw it. Imagine if I'm going to draw a molecule with 20 or 30 carbons, how long it's going to take me to do it, right? So it's not really good. So this is the complete structure. I can take it down to the condensed structure, like writing CH2, CH2, 1, 2, 3, CH3. This is the condensed structure where I eliminate all the carbons. And this is the structure, the chemical formula. Okay? Then we are going to introduce the way that we are going to be doing that, mostly the skeleton structure. The skeleton structure. In the skeleton structure, we show the symbols of heteroatoms. Non-carbon, non-hydrogen. So in organic molecules, you are going to have molecules that have, in addition to carbon and hydrogen, they are going to have elements like oxygen, sulfur, chlorine, so forth. So in the skeleton structure, we show the symbols of those. We show the bonds to heteroatoms. Okay. We show the chemical bonds, but not the symbols of carbon. Okay, I'm just going to draw it here. Well, for this molecule, this is the skeleton structure. 1, 2, 3, 1, 2, 3, 4, right? 1 carbon, 2 carbons, 3 carbons, 4 carbons. Each end is a CH3 group. Each corner is a carbon, and it can be either CH2 or CH. In our case, it's a CH2, right? So this piece here is a CH2 group, and this piece is a CH3. So one of the basic things that we need to learn is to be able to see the skeleton structure and translate it into this structure, or the molecular formula. That we need to master as soon as possible, because from next week we are going to be using this kind of skeleton structure, because they are going to be easier to draw. Okay? And having done that one, we can, unless you want to stay, we can go. You want to stay? You can continue. Okay, people, I'll see you in just